Swayam Prabha. Digital India. Educated India.
Welcome to Structural Dynamics class. In this class, we will discuss the theory of seismometer. So, how we use the principles of dynamics in designing an equipment which measures earthquake record or earthquake ground motion. So, before going into the theory, let us watch some earthquake ground motion records and equipments, how they are recording this one.
Scientists record these waves on a device called a seismograph. These zigzag lines show the strength of various seismic waves.
So, let us discuss the various terms which are used in this measurement. So, first one is called seismograph. So, seismograph is an instrument that records earthquake ground motion in a particular direction as a function of time. So, that is called seismograph. And then seismoscope. This is a simple seismograph that records earthquake ground motion on a plate without time marks. So, thus it enables one to find out peak motion but not the time history of the ground motion. And third one is seismogram. Seismogram is a record. So, it is a record, that is time versus amplitude of ground motion recorded by seismograph. And the fourth one is seismometer. A seismograph consisting of a pendulum or sensor part of the seismograph, that is called seismometer. These are the terms. Now, what is the principle of this one? So, let us consider a single degree of freedom system oscillator which has mass, a spring and a dashpot. So, something like this. So, we use the basic structural dynamics principles of single degree of freedom system and try to devise an instrument. Okay. So, this is a free body diagram of that. Say if we give motion x, so it is a free body diagram, and the relative displacement between the ground and the center of mass is given as z. So, as the ground, hence the base of the oscillator moves, a relative motion takes place between the base and the mass of the oscillator. So, base and the mass of the oscillator. Through mechanical, optical or electrical means, it is possible to record the motion of the mass with respect to its base. So, that means what? We cannot independently record the motion of the mass, but we can record the relative displacement between base and the mass. So, let y be the ground displacement, which we do not know. We do not know how to measure it right now. And let x be the displacement of the mass, and z is the relative displacement between these two. So, if we draw the free body diagram, so what we get is, let y dot and y double dot are ground displacement, ground velocity and ground acceleration respectively. X dot and x double dot are absolute displacement of the mass, absolute velocity and absolute acceleration of the mass itself. So, what we can do is, we can write, we cannot measure x directly, we cannot measure y directly, but what we can measure is the relative displacement between these two. So, displacement x minus y is a relative displacement, x dot minus y dot is a velocity relative, and then x double dot minus y double dot, this we can measure. Now, if we draw a free body diagram, so what we get is, say m x double dot plus c into x dot minus y dot plus k into x minus y is equal to 0. So, mass is moving by x double dot only. So, inertia force is related to the absolute motion of the mass, which is x double dot, absolute acceleration of the mass. And then damping and stiffness are relative terms. So, that means what? As long as there is extension or compression in the springs, then only force in the springs will appear, otherwise it is 0. So, that is why mx double dot plus c into x dot minus y dot plus k into x minus y is equal to 0. So if we introduce a new term which is minus m y double dot in the equation, so we will get this on the left side and the right side. So if we call this x minus y as z, x dot minus y dot as z dot, and x double dot minus y double dot as z double dot, so we can rewrite the equation like this. So this is governing differential equation for single degree of freedom system under earthquake excitation. This is similar to that. Now comes to the solution of it. So how do we solve this one? We will approximately, we will assume that y of t is equal to y0 is the amplitude of ground displacement, sin omega dash t. So this omega dash is forcing frequency, that is our ground frequency or frequency of the ground motion. So if we divide this above equation by mass, we get z double dot plus c by m into z dot plus k by m into z is equal to minus y double dot. So that is, if you double differentiate it, y0 omega square sin omega t. So minus minus will get cancelled. So we can write the terms like c by m is 2 zeta omega n and k by m is omega n square. So this, from the first principles of structural dynamics, we already know that. So the above is a linear non-homogeneous differential equation with constant coefficients. Again we know this one. So its solution consists of a homogeneous solution or transient part and a particular solution which is steady state part. So this zt homogeneous part will be there and zt particular integral part will be there, both will be there. So but we know that this homogeneous part will die out because of the presence of damping, so we will not consider that. So then particular integral part will be z particular r square by under root 1 minus r square whole square plus 2 zeta r whole square into y. So y0 sin omega t minus phi. So if there is any confusion in this equation, you may refer to single degree of freedom system forced vibration, damped forced vibration class. Then due to damping, the transient motion dies out, hence neglecting the transient solution. So we have particular integral solution this. So here phase angle phi is equal to tan inverse 2 zeta r by 1 minus r square. R is a frequency ratio. Here in this case r is omega bar by omega n. Omega n is a natural frequency which comes from under root k by m, and omega bar is the earthquake forcing frequency. So we can write it like this: amplitudes of both the vibrations, if we do z by zt maximum value is equal to r square by 1 minus r square by under root 1 minus r square whole square plus 2 zeta r whole square. So let's try to understand some special cases in this equation. If you look at this equation, there are some special cases in this equation. So these special cases come from the ranging of R value. So R means frequency ratio. So if forcing frequency is very less than natural frequency, so that means what? It is almost in the state of rest. So that means R value is much less than 1. So that means it is equivalent to 0. So then z by z double dot is equal to 1 by omega n square. So it is something like this. You can see z, if we measure z, that means it is equivalent to measuring acceleration if you multiply that z value with omega n square. So the output is proportional to ground acceleration. So what we are measuring, actually we are measuring with the instrument z value only, that is relative displacement between mass and the ground. So with that mass and the ground relative displacement, if I multiply with omega n square, I am getting acceleration value. So the output is proportional to ground acceleration for the frequency range that are there are no distortions in the time history. So thus the instrument works as accelerometer for small values of r. So the natural frequency of the instrument is usually kept in between 25 to 50 hertz to measure acceleration. So accelerometers will have this range. So if we plot that z curve, okay, so by double differentiating y, So what we get is, so 1 by omega n square y. So y double dot is equal to 1 by omega n square y. So then we back substitute that, z by y double dot is equal to 1 by omega n square under root 1 minus r square whole square plus 2 zeta r whole square. So now in this, if we substitute r as 0, so denominator term, this will disappear 0 and this will become 1. So z by z y double dot is equal to 1 by omega n square. So that's how if we measure acceleration or measure z, we are getting ground acceleration from this one. So it is something like z by y double dot is equal to 1 by omega n square. So y double dot is equal to omega n square into z. So we are measuring z. So multiplying with omega n square is giving us ground acceleration. So hence this is called accelerometer. Similarly, we measure displacement. How do we measure displacement? When forcing frequency is much larger than natural frequency of the system. So r square is much greater than 1. So when r square is much greater than 1, so the ratio is same, r by 1 minus r square whole square. So what it will remain is, so this value is approximately equal to 1. So if you look at, if substitute some value here, say 100, r value has 100, and then check, we will get approximately numerator and denominator same value. Damping will not have any effect there. So this z by y is equal to 1. So that means what? For higher frequency excitation frequencies, whatever displacement we are measuring, that is equal to relative displacement we are measuring, that is equal to ground displacement. So the output is proportional to ground displacement for the frequency range such that r is large. So for this frequency range, the output will look similar to ground displacement and there will be no or very little distortion. So the instrument is called displacement meter. So this is a displacement meter. Z by y is equal to 1. So z is equal to y. And third one is velocity meter. Velocity meter, like when frequencies are same, forcing frequency and natural frequency are same, then r square is equal to 1 or r is equal to 1. So what will happen is, the term will under root 1 minus zeta square zeta r will remain. So 1 by omega n into r. So we will be left with z is equal to 1 by 2 zeta omega into y dot. So then we get y dot is equal to, from this we get y dot is equal to z multiplied by, as you can see this equation. Okay. So y dot is equal to z multiplied by 2 zeta omega n. So we know zeta value, we know omega n value, we were anyway measuring z value. So we get velocity. So hence this is called velocity meter. So in summary, by using principles of single degree of freedom system, we are understanding how to measure earthquake displacement, velocity and acceleration. So in a way, earthquake acceleration is measured when r value is very low. So that means forcing frequency is much less than natural frequency of the system. So this is accelerometer. And on the other side, if say forcing frequency is very high compared to natural frequency, it is displacement meter. And so for accelerometer, stiffness should be very high. Stiffness of the structure is very high and mass is low. Less mass, high stiffness. And on the other side, displacement meter, more mass, less stiffness. So these two are the extreme cases. So accelerometer and displacement. In velocity, frequency, forcing frequency and natural frequency, if they match, that means at a resonating condition. So we get a special relationship between ground displacement, that is relative displacement, and ground velocity. So we have studied these three cases of accelerometer, displacement meter and velocity meter in the seismometer, and the concept what we have used was undamped forced vibration of single degree of freedom systems.